The broadcast is now starting. All attendees are in listen-only mode.
Right, good morning everyone. Welcome to today's webinars. The title is Weldment Analysis with SolidWorks. I'm William Goh, your instructors. Well, before I want to start, I want to credit these slides and the information of these slides to Stephen Andersby from the SOC Systems. It's a simulations product managers. Right, basically these webinars will be a 1 hour webinars. It's not how to use it, it's more like the introductions to analysis of Weldment with SolidWorks simulations. So a little bit of introductions here. In SolidWorks simulations, we have 3 types of elements. Okay, if you have experience with SolidWorks simulations before, you will know that you have 3 types of elements. The first type is the solids element. The second is the shells element. And the third one is the beam elements. Well, the question here is that which types of the elements is best to use for weldment frames analysis? So, solids and shells element. Solids elements will have excessively large number of elements. Not really a realistic approach when you are doing weldment, especially for very big or very complex frames. While time consumes to mesh and solve the whole frame's element. While as for shell, although it doesn't include that much of elements, but it's still, you need to prepare all the surface geometries. You need to verify what are the contacts between them, what are the thickness of each of the elements, so that it will to be made into shell elements. So it's also time consuming, but in terms of not in terms of solvings and not in terms of meshings, but in terms of producing the shells element to be studied. Well, then here comes the beams element. Same as the sheet metals, when you are doing analysis for sheet metals, the shell elements will be the natural choice, or should I say the default choice for the analysis. As for the beams, as for the weldment, if you are using a weldment models, the default choice, the default choice for the elements is the beam element. So this is an example of the frames, the weldment frames, and this will be the measures. So I will explain more on this in later slide. So if you are not using a weldment models, what if you are extruding a profiles, or you use an imported bodies, you download the frames from any 3D content centers or any CAD website. You download the files and you want to do analysis on those particular frame. Well, of course, since it's an imported file or it's an extruded bodies, extruded solids, the default choice will not be a beam element. So all you can do is you can just right click on those particular solids or those particular components, right click, and you can always treat as a beam. So it works the same as the default choice of beam elements, right? So the analysis types that support for the beams elements are statics, frequency tests, buckling tests, and nonlinear tests. Well, of course, bear in mind that the large displacement in statics are not supported for beam element. So here are the four examples. Here are the 4 supported modules of simulations which you can use beam elements: the statics, the frequencies, the bucklings, and the nonlinear. So in some cases, such as the frequencies or the bucklings, it is highly recommended to use the Weldment frame, right? So because those will consume a lot of times, if you are going to run those studies in solid case, in solid meshes or in solid elements, it will consume a lot of time. So of course, some of the things that you need to be careful, some of the things that you need to bear in mind is that in order for you to get accurate results, the length of the beam should be large compared to these dimensions of the cross-sectional areas. So if this is the cross-sectional areas, the length of the beams should be relatively longer, should be relatively larger compared to the cross-sectional. This is because of the solvers, the mathematics behind the solvers of the beam element analysis. So beams, of course, here a little bit of theories here. Cross-sectional properties. Beams are structural members with the cross-sectional properties accounted for in the beam definitions. So cross-sectionals are perhaps not needed to be reflected in the finite element measures. It's greatly simplified for model preparations and analysis. As you can see here, in the first examples, in the first beams, it's considered as a beam, as a solid element. So you will notice, you will see all the details of the profiles and all the details of the whole length is being considered in the analysis. Of course, as I mentioned earlier, this will take a lot of time. This will be time consuming for you to solve. Well, in second case, where we consider this as a beam element, so in the studies, it will only consider it as cross-sectional areas with a length of the beam. Okay, simplifying it with minimum losses of the accuracies. So for your information, if you look into your SolidWorks, or this is the structural members, and you will see the joint at the two ends of the beam. Of course, if you have any turns around in the middle of the beams, they will add another joints in the middles. So, and in the meshes case, it will only show a cylindrical extrude, a cylindrical bar, cylindrical bars as the meshes. So it reads as a beam profiles instead of considering the whole cross-sectional area. So in beam, there are some assumptions that we need to know. It's a general, in other words, it's a general knowledge, general information of the beams in our case. So the beam elements have 2 nodes and 6 degrees of freedom per node. So each element is defined by a straight line connecting 2 joints at its end. Okay, just as the previous case is considered as a beam element with 2 joints at the end of the structural members or the meshes. So then, what about curvature structural members? What about curved structural members or non-straight structural members? Okay, so it will consider that as many little short straight beams or straight beam elements. In this case, these are being shown in small straight beams elements connecting each other from one point to another. Okay, this is how a beam studies. This is how SolidWorks simulations look at the curved structural members. Okay, so further small assumption is that the constant cross-sectional areas is being considered in the whole beam elements in the whole length. Okay, is considered as only the constant cross-sectional. Measures each structural member with a number of beam elements. Okay, each of these is considered as one beam element. Alright. So beam element is represented by a cylindrical regardless of the actual cross-sectionals, which I mentioned earlier, which I explained earlier. Okay, so it simplifies the whole models for study purposes. Of course, the accuracies will not be that high compared to actual cross-sectionals, but it will have its accuracies regardlessly. So let us go to the examples. So the first example is a simple frames. It's simple frames that we have here. So there, as you can see here, each of these are a beam element. Okay, since model this using a weldment, so we have that as a simple beam elements with these symbols. If you notice this symbol, this is a beam element symbols. So all the joints are defined as additional types here. Okay, additional properties here as the joint groups. Okay, you can edit it and you can right click and edit it. Later maybe I can show it in the SolidWorks. So when you measure it, okay, when you create the meshes, it will show in beam elements for each of these, okay, with small cylindrical elements, which is the beam elements for the whole weldment frames instead of the actual beam. Okay, as you can see here, and all those points are the joint. So the results, let us look at the results. So the results of each element are presented with of the local directions. These are the results types that you can have: the axial, the bendings in direction 1 and direction 2. So maybe you wonder what is direction 1 and direction 2. So direction 1 is the directions of the longest straight edges. So of course is in the horizontal or the vertical directions. So some of the examples here will be the first 3 examples, where the longer edge it will consider as the direction 1, okay, and the direction 2 simply means that in other directions, verticals or the horizontal directions, which have the shorter edge. But what about non-straight, not perpendicular profiles, such as a curved profiles or a round profiles? Well, don't worry about that. SolidWorks simulations in the weldment, when it is reading the beam elements, it will automatically consider using other criteria to consider the directions 1 and the directions 2. Okay, so it's basically still in the horizontal and vertical directions. Okay, in these 2 cases, the directions 1 will not be the longest straight edge anymore. Okay, but it will use another criteria and optional criteria to clarify what are the results for these 2. Right. So of course, for beam elements, for weldment analysis, we can call out the beam diagram for each of these. So the beam diagram that we can call out are the shear diagrams along the beams, the moment diagrams, and the top, and also the axial force diagram. Okay, these are some of the examples that you can see here. Okay, simply pick on the beams that you want to know the shears, the moments, the torques, or the axial force diagram. Okay, you can simply call that out just with 2 clicks or 3 clicks. Okay, so let me go to the examples. Let me have a look of how does it goes. Okay, so this is the frames. Okay, a simple frames that I mentioned earlier. So let us look at the interface of the simulations. So as you can see here, we have all these being shown as the beam element. Okay, because I'm using this as a weldment, and automatically by default this will be my beam element. So these are the joints together. These are the joint. So if I edit it, you will notice that you can click on calculate and it will automatically select all the joints, all the possible joints for you. So if it's not, you can still add in your own manually. You can manually add in your own joint, right? And the force is exerted on beams, okay, instead of surface. Of course, if you want to put on surface, yes, you can still do so. Okay, you will notice that this is an additional thing if you are running the simulations in the Weldment, right? So of course, running the mesh, you will have the elements represented in cylindrical blocks, Weldment blocks, instead of the actual profiles. And running it. Okay, this will give you the results. Okay, so as I mentioned earlier, the shear moments plots. Okay, you can have it in the axial force, the shear force in direction 1, direction 2, and what is direction 1 and direction 2, I have already explained earlier. So you can either select on all the elements or simply select on the particulars beams that you want to know the beam diagrams. Okay, so let me show this. So you will see this, the beam diagrams. I can simply change it to the Excel force instead. Right, so it will give you different results, okay, depending on what is your outcome. Right, so let me go back to my slide. So we have done the first examples. Let us go to the second examples, which is the more complex structures compared to the first one. So these structures, we have many more members, and some of the members which does not meet together. For example, these two structures does not actually mix together with the bottom structures. Okay. So how does the noded joints being joined together? They consider the center, the shear line, the shear axis, or the center axis of the beam. So since these two center axes does not coincide together, we might have some problem. So of course there are ways to tackle this kind of issues. So instead of putting equals to zeros, instead of putting touching beam, we assign a clearance. We assign a clearance of the center lines, or the center lines of the beams, or the shear axis of the beams, and do a new calculations, recalculations on that. So it will consider these two joined together, but the joining points will be at the beam. Okay, so so a little bit of the discussions of the results here. So this will be the results, and same as the simple frames, you will have colorful frames results here. Okay, so if you look here, this is how the beam frame deflects the deformations, or this is the stress, the upper bound axials, and the bendings results. And you can check on the displacement, and of course, you can also call out the beam diagrams for each of these. So this will be a more complex, and the only things that is crucial here is the non-joining beam together. So maybe I can show you the examples. Alright, so this is the more complex frame compared to the simplest frame, compared to the first examples. So if you see here, we will have Let me run the meshes. Okay, as you can see here, they add an additional beam here, okay, to tackle the issues since these two joints are not connecting each other. So of course, if I edit the groups, you can see that I assign a 400 clearance, okay, and do a recalculations to these two joints, or else it will not show any joint here. Okay, or else it will not show any joint here if I check on the equal to zeros touching joint. So so this is how to tackle the issues. If you check on this, you will notice that how check on the neutral axis or the shear axis, you will notice that how these two being the intersections of each of the point is the joint, is where it plays the joint nodes, right? So looking at the results, you will have it's basically the same things as the simple frames where you can show the truss, the displacements, and the beam diagram, okay, for the frame. Okay, so it's basically the same, and of course you can also show the beam diagram. Okay, selected. Let's say I want to know the moment in directions 1 for okay, so it will show you too in the first directions. Okay, the moment diagrams of the first directions, right? So it's the same. It's also the same things as the first examples. So let's go back to my first examples. Sorry, my slide. So the third examples will be the truss. Okay, when are we going to use truss? So first of all, you need to know what is a truss, what are the properties of truss, and what are the criteria where we need to use truss. Okay, for some of the bridge structures where they are constructed up by more than one or the triangular structures, so we can consider that as truss. Well, for informations, beam elements, they consider the shear force and moment force, while truss is a beam element where it can resist the axial deformations on it. Okay, so we does not consider the shear force and the bending moment here. So we only want to know the axial deformations in the truss case. So these examples consists of 36 Weldment bodies, okay, and one surface bodies at the bottoms, okay, as the platform. So we can change it. You can run one times of beams and we get the results. And later I will show you the results between these two, comparison between the beam results and the truss result. So once you change all the structure member to truss, okay, of course it does not means that you need to change everything. Only those particular triangular structures which you only want to know the axial deformations, where you don't want to consider the shear and moment forces. So you can just select it on those particular bodies and click on truss, and you will notice that the icon change. Instead of beam, it will consider as a truss icon. Okay, this is the truss icons of SolidWorks simulations. So as you can see here, this is the displacement results in two cases. One is the beam cases, and another one is the truss cases. So for the beam cases, it considers the shear force and the moment and the bending moment. That's why you will see some unnatural bending, some unnatural deformations on the beam, which is not the actual case. So in this kind of case where there are struts and there are truss members, we need to use truss so that we will have a more realistic results. We have a more realistic results here compared to the beam element. Alright, you will notice it is quite clear here. Okay, and even the results will be different. Alright, so basically there is only three examples that I'm going to show. So don't think that don't thought that these webinars were some sort like trainings. It's more on an introductions to beam analysis, to weldment analysis, for anyone who have experience in SolidWorks simulations. So I will call this as an end. So thank you for the time. And if you have any questions, if you are doing any simulations, if you encounter any problems, you can always drop me an email. Okay, this is my email, and these are my numbers. So if you encounter any issues in simulations, not just beam analysis or weldment analysis, you can always drop me an email. Okay, we will support you. All right. So thank you very much. So I will end this webinar.